choose your own molecule one?
Let's talk about the analysis of an organic compound. Thanks for, I don't know if you did that or if that was already here.
That was already there.
Thank you to the gods of this room for leaving this paper towel. So you had an assignment that was due last week, and I apologize for not talking about it last week. I think you guys know that this classroom is a little bit more lax when it comes to due dates, and I'm not totally upset if you haven't even considered this assignment yet, because there are still reactions that might be useful for you to apply here. So I would like for you to have all of the reactions at your disposal before doing this. The next of our assignments on analyzing an organic compound is proposing a synthesis. And I do want to talk about this because it's only my second semester giving this assignment. And over the summer, I had a very small number of students in this class. One student, or maybe more than one student, did not propose a synthesis with this assignment. They proposed a retrosynthesis. So if you have chosen this compound, A, proposing a synthesis is converting this into compound B. A retrosynthesis is taking it from something else and making your compound. As long as you do one for each assignment, I guess I'll be happy with it. But I would like to see them in order so that it's a little bit easier for me. Otherwise, I'll just be leaving this comment, like make sure you do, if you give me a retrosynthesis for the synthesis one, then make sure you give me a synthesis for the retrosynthesis one. Retrosynthesis is having something in mind that you want to make and deriving a way to get there. A synthesis is having something ready and available and turning it into something new. Some of the input in here is you must use a reaction demonstrated in class. That's one of the reasons I'm okay if you haven't done this, or if you want to resubmit it if you have already done it, because we're learning more reactions today. Also, this only needs to be one step. I guess I don't explicitly say that. I do explicitly say show all necessary reagents and any necessary steps. But we've done a lot of reactions that have aqueous workups. So you have to show 1, give me the reducing agent, 2, give me the aqueous workup. But you don't have to do more than one step. You're welcome to, but I'm really just looking for one step in a reaction. Does that sound okay? Killian, you had a question?
So on our projects, if we say we're trying to synthesize this molecule, are we saying that incorrectly? Are we trying to retrosynthesize a molecule?
Your molecule of choice, you're going to do 2 things with it. You have 2 assignments remaining, plus the reflection. You're going to show a synthesis with your molecule, and you're going to retrosynthesize your molecule. Just one step in both directions.
General terminology, so either in the lab or on our own research projects through the program. If we're trying to get to a molecule, is that called the retrosynthesis of evergreen oil or dihydropyridine?
It depends on your perspective. So for instance, this is a synthesis of A, but I don't know what Z is. I want A, so I'm going to try to retrosynthesize it. I'm going to figure out what it can come from. So for your example, you're saying, I want to make wintergreen oil. Sorry. I want to make wintergreen oil. If that's where you're starting from, then yes, you have to retrosynthesize what do you want to make it from. But if you're looking at this as I have salicylic acid, and I can do a lot of things with salicylic acid, but I want to make wintergreen oil, then that's a synthesis. Synthesis and retrosynthesis describe a reaction. Although if you wanted to, you could do multi-step. You could say, I can make A from Z in one step, I can make Z from Y in another step, I can make Z so on and so on and so on. But all I'm looking for is that you can give me one retrosynthetic step, which just means identify a functional group you know how to form, and form it from a precursor. Show what it would need to be made from. And only one synthetic step. Take a functional group you see in your compound that you know how to react with and change it. And be creative. Don't take the easy route and just do oxidation or reduction. Do a Wittig reaction. Do transesterification. All sorts of reactions at your fingertips to do. Did that help answer your question about using synthesis and retrosynthesis appropriately?
It did.
Great. All right, any other questions on this assignment? All right. Oh, wow. Okay, so we're going to be learning new reactions today about carboxylic acids and their derivatives. On the back side of this sheet, it will demonstrate why they're called derivatives. But if you haven't already, I'd like you to get started on filling out this form just on the top side. Figure out what common carboxylic acid can be made in the center here and the reagents that are needed. I'll give you guys the next 10 minutes to go through your notes. These are all review reactions except for the one that says CO2 as a starting material. And I did want to leave a note. You'll see that these all form the same product. And so they all have to have this benzene ring in it, the pH group. But it's the one on the top right that says this is the only one that must be a benzylic reaction. All of the other ones, they don't need the pH group. They could just be any other R chain. They just are the same R chain. And I forgot to upload this. I will upload it to Canvas right now. So 10 minutes. Feel free to work collaboratively or kind of in your own space, whatever helps you learn the best from this.
See you in 5 minutes.
I'll see you in 5 minutes. What does that mean? All right, it should be up there now on Unit 4 towards the top. Mm-hmm. As well as KMNO4. Pretty much anywhere you see chromic acid, you can substitute for KMNO4, potassium permanganate.
Strong oxidizers will do that.
Correct. But I just don't. Yeah, you'll see us use chromic acid more than potassium
Yeah,
permanganate.
because it came in a 4 requires like a long period of time to react.
At least for the benzylic oxidation. Not always for anything else, but I don't know. I think maybe it's vibes. Kind of like how chromic acid looks.
Could you explain my hands? This
Yeah,
or this,
yeah.
but one of them has to be with this in order to do a benzylic hydrogen into.
Okay, no, these are the same. Those are different ways of writing
Oh.
it.
So this
Or this.
or
Yeah, like this does the reaction and this does the reaction.
so this, aka or.
There you go. I like that.
Hey John, I was not seeing it on Canvas. I keep clearing it and pasting it. You got it?
Under module 4. Right at the top of module 4. Yeah, it's not showing up for you. Is it the Wi-Fi? You said you reloaded everything. Let's try this. Can you access files on Canvas? Kayla, why don't I just share it with you directly?
Yay, thank you so much.
That's pretty strange. Oops. Oh my goodness. All right. Sent, but you can probably expect it in like a year or two.
Oh, here it is.
It loaded on Canvas now?
Yeah. Well, you're
Oh, the email came that quick?
Yeah.
Wow.
Thank you so much.
You bet. Yes.
I didn't feel very creative.
Now, can you solve for that? I'll give you a hint if you want it.
Yes.
It's a 1-2 reaction,
Okay.
and 2 is the aqueous workup.
Okay.
Is yours coming along?
It's coming along.
Good, good, good. No. Yes. No, perfect. Yep, that's the most it can do. We call it a mild oxidation agent for that reason. Good. You bet. And there is another answer for this. So KMNO4 does work. So does this. It's a both situation. You could use either one.
Fine, you're right.
Great job. Are you thinking about how you can get here?
Yeah.
Think about what you have with that reagent and what you need to get to that final product.
Hey, we're doing this today?
We're not doing that today. I uploaded a video actually.
Is that the one you sent in the email inbox, the inbox message?
Maybe.
Was that you who did the amine mechanism?
I didn't mail it to anybody though. I posted it on Canvas. I might have
You sent-
messaged
Okay.
to say that I posted it. I can't remember.
Mm-hmm.
Is that right? Good. Yes. Now can you show what that makes?
So
Yes.
got this. That's exactly it. They're all making the same product. Yeah, exactly.
Okay, that was screwed. I think that was my biggest hurdle. I was like, I don't even know. Oh wait, it's called carboxylic acids. That's what we're doing.
Yeah. To be fair, that is a big gap, right? You have all these different starting materials and no reagent given. Off to a good start.
Oh, we're doing. Shoot. I should know.
Is that
Carbon has like no.
This is.
I mean, it's got a
But they're like all unbound.
true. So it's got a partial positive.
Yeah.
Okay.
Should be electrophilic.
Yes.
So the ring would have to act nucleophile.
To make a carbon-carbon bond.
Yes.
Good. So what nucleophiles are good at making carbon-carbon bonds? Is this OH or Cl?
I was trying to do Cl.
But Cl also, so it's a partial positive on here.
Right.
So that would also be electrophilic.
So you need something slightly electron donated.
Or like aggressively electron donating.
Yeah.
You could try this. I mean, you've got notes as well. So look for carbon nucleophiles. You could also Google that and just see what the internet pops up with that sparks a light.
I feel like I'm being way too vague.
This won't do it, and actually this won't do it either. You're not being vague. You're being very specific, but those reagents just won't do it.
I need one here or is that just forming diol?
That's the diol. Yeah. So
So do I need this and something else, or is this just not?
it won't do that. It's hard to make an acid in basic conditions, but you do want to be looking at reactions with aldehydes. You've got an aldehyde starting material. There's another place that you could look, which is on the unit learning objectives sheet. If you know what functional group you have, you can look for reactions with it to make some new functional group. Although I'm not the best at putting all the reagents in there all the time. But yeah, this is a good sheet. Where can you go from an alcohol? Where can you go from an aldehyde? Where can you go from an alkene? All reactions we've reviewed. It's a good start. But I need to be able to form a carbon-carbon bond, right? So would this be able to attack to form a carbon-carbon bond? Something could attack it, sure. It'd be like acyl addition.
Something will attack this and then kick this to here.
Exactly. Acyl addition. So how can I make a group on here that's good at making the carbon attack? Because I don't want any oxygens to attack. I don't want any nitrogens to attack. How can I make this a nucleophilic carbon? And I give the same tip to think of. If your notes don't spark it, see if the internet will. You on your last one? You're still up here.
Yeah.
This is very close. This reagent with a different
Oh, is it reductive?
reductive ozonolysis gives us aldehydes.
Oh, okay.
We need a different type of ozonolysis.
So can
Is that to me?
Oh, you're saying how do you kill it?
I forgot how to do this. We're doing this. I'm supposed to do this tomorrow. Hey, how do you do this? Where do I look?
Well, you can look at synthesis of aldehydes because this is also a review reaction. All right, that was about time. Now, I actually would like for you to spend another 5 minutes on these bottom three. These are all reactions we have seen with carboxylic acids as well in different sections. Actually, two of them are in the same section. One was in our last section with aldehydes and ketones. So I guess I'll give another 5 minutes. You know what? You can keep working on all of the ones you want, but I do want to draw your attention to the bottom three. See if you can solve those if you haven't already. This is going to have nitrogen attack.
Yeah.
I want something with carbon over the electrons. So what is carbon more electronegative than? There's not a lot. There's one that you should think of for sure. Carbon is more electronegative than its favorite buddy. difference in electronegativity. It's also less electronegative. It's more electronegative than most of the rest of the periodic table.
Oh.
Everything that is below it and to the left, which are all what type of elements? Yes. Metals. Metal. Carbon is what type of reagent? That's an example of one. Metal, organic, organometallic. Yep. This does not react. If it did react based on other things
This
we've
way?
seen, this would give us an alkane, certainly not an alcohol, but it actually doesn't react.
Well,
Can't have basic conditions with a carboxylic acid.
hold on.
I'm waiting.
Top one. Okay, could be anything. Only works for aldehydes or ketones, which it is. I believe it could.
I believe you're wrong. This is a fun game. Let's say other things we believe in.
Well, at least I'll explain it.
That's what you think. Why was I so heavy on the aromatic theme today? What?
Where'd you put that?
I've got it over here, but Maddie actually likes to download hers. Do you want this, Maddie?
No, I'm good. I can download it on set.
All right. Maybe you can, maybe you can't. I got two that we're able to and one that won't.
Oh, okay.
Maddie, we also talked about the analysis assignments.
Yes.
One is a synthesis, take your compound to something else. One is a retrosynthesis, make your compound from something else.
Oh,
It doesn't need, this was another thing I forgot to say, it doesn't need to be a plausible thing. Like a lot of you have chosen drugs or like commercial products. You don't need to find something that is done to synthesize your compound.
Oh, it can just be.
Just take a reaction you know and show it. Yep. Doesn't need to be something done in the real world, just something that's done. Just something that's plausible.
If there's a reaction, like let's say you had a really difficult molecule and there was like a reaction that you didn't have that you would need.
I want it to be one that's demonstrated in class. So something that we've shown. I want you to use the reactions we've done in class. All right, here's the deal. I want to get moving on, and I'd actually like for each of you to come up and solve one of these. I'm going to pause the camera so that you feel a little bit more comfortable coming up to the board, but I'd like you to take a stab at one of them. Oh, that saved me the work of writing it all out. Thank you. All right, let's talk about it. I know a lot of you are going to be copying some of this down. I'm going to start from this reaction. Oh, I guess I didn't have anybody fill it in. The product that these all form is
Benzoic acid.
benzoic acid. Killian, you have a question?
Is that one on the right one too?
Is this one on the right? 1, 2?
Or is it all at once?
No, this is all at once.
Oh,
Yep. Okay, there are some changes. I didn't catch all of them, sorry. There are some changes that we need to make. First, let's look at this reaction coming, well, actually, let's go to this one that's on the top right. I gave you guys that note on your worksheet. This is the only one that must be benzylic. Why is that?
Because it's splitting off
Good. We're charring everything else. We're oxidizing the benzylic carbon. None of these other carbon chains need to have a benzene ring. I just gave an example where they did so that they all formed a common product. But all of these other reactions, they happen on their functional groups regardless of whether they are benzylic or not. This is benzylic oxidation. It's the only one that must be a benzylic position. There's another reagent we could use. What else could be used here?
KMNO4.
We can also use potassium permanganate. It's just much more common that I will show you chromic acid. All right, now let's move counterclockwise. This is called oxidative ozonolysis, specifically of our alkenes. I just taught my Ochem 1 this reaction last night. There is another reagent that we can use here.
Hot KMNO4?
Hot KMNO4. And to be fair, we also talked about how for potassium permanganate to do benzylic oxidation, it needs to be boiling for like a day. So these both can use hot potassium permanganate.
The whole reaction needs to boil for a day? Or just...
Yeah.
Okay.
This is also oxidative ozonolysis, and in the same way, it also can use hot potassium permanganate as another way of getting there. We know that potassium permanganate is a strong oxidizer. You might not look at ozone and peroxide and think strong oxidation, but they work with those pi bonds on the alkene and the alkyne. This reaction is actually not quite correct. PCC is an oxidizer. It's not a strong oxidizer. This will leave us with benzaldehyde. Instead of pyridinium chlorochromate, we need chromic acid or potassium permanganate. Pretty much anytime you see chromic acid, you could swap it with potassium permanganate, hot. Which we see, again, oxidation of the aldehyde to the benzoic acid. We need chromic acid there as well. Remember that when the alcohol is being oxidized to the carboxylic acid, there's an intermediate aldehyde that then gets oxidized further to the final product. All right, now there was a new reaction that I covered in here, and Jacob was able to solve this one. We know that the common product between all these reactions was benzoic acid, and I gave you this hint about CO2 as a precursor. That CO2, if we draw it out, carbon dioxide, looks a lot like the carbon of a carbonyl, especially the carbon that will become a carboxylic acid carbon. It's already bonded to two oxygens, and it has double bonds to both of them. So if I can break one bond and then protonate it, I'll be done. That means that what I'm missing is a benzene ring. And I need to be able to form a bond between the two carbons. This is essentially acyl addition. I'm doing an acyl addition to a dicarbonyl, which will leave me with a monocarbonyl, if you will. So what kind of reagents do I have? Carbon dioxide, nucleophilic or electrophilic? Well, let's talk about from the carbon, because I want to make a carbon-carbon bond. Is the carbon nucleophilic or electrophilic?
It's supposed to be electrophilic.
Electrophilic. It's got a strong partial positive because the oxygens are pulling on it. That makes it an electrophile, which means my aromatic ring needs to be a nucleophile. We actually know how to make aromatic rings nucleophiles from EAS reactions. I could put an alcohol group here or an amine group here. The problem is I don't want an alcohol or amine on my benzene ring. I want it to just be benzene at the end of it. So I want to make a carbon nucleophile without needing to activate it by some sort of EAS reaction. The only other carbon nucleophiles we've looked at are organometallic reagents. So something like carbon to a Grignard or carbon to a lithium. These are strong nucleophiles that form carbon-carbon bond. Carbon takes the electrons because it's more electronegative, and it breaks one of the CO double bonds. That doesn't leave us with our final product. That leaves us with a carboxylate. Plus we have this balance of charge, O minus, MgBr plus. So I can't make an acid compound in nucleophilic or basic conditions, which is why this reaction must be first organometallic, second H3O+. I do want to highlight that this is able to change forms depending on what exactly you're starting with. And you all are familiar at this point with synthesizing organometallics, which means you're often not starting with carbon dioxide, you're starting with an organometallic. So we can write this another way. We can write that we have the organometallic, and then we add first CO2, second H3O+, and we get our carboxylic acid. Seem fair? Both reactions are saying first, mix the organometallic with CO2. It's just a matter of which reagent is written over the arrow and which reagent is written on the arrow. Those of you that took my OCHEM 1 class, we talked about this. The arrow is kind of meaningless. This could all have been written as a sequential thing, but it gets a little bit awkward to write sequential reactions if it's not over the arrow. So totally interchangeable, just depends on how it fits in your synthetic scheme.
An alcohol makes a ring a nucleophile?
Yeah. According to the EAS reactions, alcohols activate the aromatic ring towards nucleophilicity.
Are the alcohols taking electrons away from the ring? Density?
Well, how would that make the ring a better nucleophile? All right, short review. The aromatic ring can act as a nucleophile. The oxygen is considered something of an electron donating group, but it's not the strongest donating group. What's a stronger donator than an oxygen group? A nitrogen group. Because nitrogens are, compared to oxygens, less electronegative, more willing to share their electrons. So that's all EAS. That's section 16. All right. Then we had these three reactions on the bottom. We had full reduction to an alcohol, partial reduction to an aldehyde, and esterification. In order to do a full reduction, we need a strong oxidizing agent, LAH, followed by an aqueous workup, 1, 2. For partial reduction, we need a selective reducing agent, or a partial reducing agent, dibol, followed by an aqueous workup, 1, 2. This is well written. I just want to make sure that that looks like a 1 and not like a D. Still kind of looks like a 1 the way I wrote it. A small thing, I see a lot of resources out there that actually write dibol like this. And I try to avoid it because it technically is miswriting aluminum. Aluminum is capital A, lowercase l. Although a lot of places will put capital A, capital L. Just a silly little thing. Esterification was a reaction all the way back in alcohols. We learned this back in the alcohols chapter, that a carboxylic acid and an alcohol in acidic conditions will give us an ester. H2SO4 is good H3O plus is bad, a more generic answer that you can put is H plus. Some of you are getting ready to do esterification reactions. All of you that are in the lab this semester are preparing to do esterification reactions tomorrow. Oh, are you excited?
Yes.
Nice. You wrote all your own procedures and everything. Good work. All right. Sound good? A review of all of our reactions to produce carboxylic acids plus a new one, and all of our reactions with carboxylic acids that we have seen so far. Flip over your worksheets to the back side.
What was the top one? The LAH called? Is it
Reduction. Reduction with a strong reducing agent.
the procedures are already written for tomorrow's lab?
You wrote them.
Well, we choose the amounts, but we already were given the stuff in the reaction.
That's good. Yeah, you're not deciding the reaction. You're just deciding how to do it. That is the point. Okay. You guys know this is my. Actually, let me ask you this: how have these reaction diagrams been feeling? Yes.
Yes.
Better than just a sequential list like what I gave you in OChem 1.
Wow.
I gave my OChem 1 group a similar one for the alkene addition reactions. There were like 8 on one, and then the 3 extra ones below it, and it was so cluttered. In fact, I don't give you guys a lot of notes on these reactions, right? Just the reagents, but for OChem 1, I'm talking about the regiochemistry, the stereochemistry, what type of intermediate does it have? One girl showed me her sheet, and I didn't actually think it was the sheet I gave her at the start because it was so full of notes. I said, well, maybe it's not working well, but I'm glad to hear you guys think it is. I think I'm going to stick with it.
Maybe it's just because there's just not so many notes, like you said.
Yeah,
You'd just be giving us the reagents. So this is
just the reagents, so it's a lot less cluttered.
Yeah.
Cooper, you wanted to add something to that?
I think I could see that would work well for this class, but not maybe for OChem 1. Because when I was looking at my OChem 1 notes, they are a lot more. I feel like the giving them is like kind of like a in the checklist almost makes more sense because then you can just make a format for how you write out each setup.
I think I might change it for the OChem 1 and maybe give
a
them.
table would be better, just because there's so much information.
Yeah, I might give them the diagram as an activity after I give them all the reactions in a list. I still had a list of all of the names and the notes. I didn't put the notes next to the diagram, but students that weren't prepared might not have been able to do that. Anyways, this was actually one of the first reaction diagrams that I tried to put together myself to make a little bit less work of our time in class. This is the carboxylic acids and derivatives relationship chart. From here, what we see is all of the derivatives, the acid halide, the acid anhydride, the ester, the amide, and debatably the nitrile. And what you can see is that the carboxylic acid can be derived into all of them. In fact, this is sometimes referred to as acyl derivation. Love to sneak some math terminology into chemistry. So we can derivatize the carboxylic acid into any of those functional groups except for the nitrile. There's no direct route from the carboxylic acid to a nitrile. There are several longer routes, but no one step. And then you can also see that all of these derivative functional groups can be turned right back into the carboxylic acid. So that's where I want to start today, is looking at the reaction that takes each of these functional groups back to the carboxylic acid, because they're all very similar with some slight differences. First, a reminder. Which of these is the most reactive carbonyl? which of these carbonyls is the most electrophilic? The acid halide, which is actually why it's organized the way that it is. The only one that doesn't fall in place because of this method is the carboxylic acid. What two groups does the carboxylic acid fall in between in terms of reactivity? Good. And you'll notice the aldehyde and the ketone aren't on here because the aldehyde and the ketone are not derivatives of the carboxylic acid. They can't be interchangeably converted. Well, I guess you could argue that the aldehyde and the carboxylic acid can be interchangeably converted. Interesting. Anyways, the most reactive of these groups, the acid halide, will be hydrolyzed. It will react with water to form the carboxylic acid in simply aqueous conditions, H2O, as well as basic conditions, as well as acidic conditions. We have to be mindful, working with acid halides, that we have a water-free environment, because any water in the presence of an acid halide can hydrolyze the acid halide to a carboxylic acid. Do you guys remember doing this in lab? You synthesized DEET by taking a carboxylic acid and making it an acid halide, making sure that there was no water in your apparatus. One of your post-lab questions was, these students set up their apparatus over the hot water bath and then ran the reaction. What happens? That water that saturates their glassware causes a hydrolysis reaction. Anhydrides are similarly as reactive. Neutral conditions, basic conditions, and acidic conditions will all hydrolyze the acid anhydride back to a carboxylic acid. In fact, the acid anhydride forms two equivalences of carboxylic acid. If it's symmetric, the anhydride forms two equivalences of the same acid. If it's asymmetric, it forms two equivalences, one of each acid. When we get to the more stable carbonyls, we need stronger conditions. Water is not a strong enough nucleophile to hydrolyze esters. So we either need acidic conditions, which is the exact inverse of esterification. So Kayla, I think you put up H3O plus here at first to show us the esterification, but if we had H3O plus, we're in an aqueous environment, and that means we're at risk of reversing it. Instead, we need some non-aqueous acid. If we have aqueous acid, it hydrolyzes back to the carboxylic acid. But we can also do this in a two-step process. First, strong base followed by an acid workup. I want to pull a little bit of attention to these two reactions. Back in the reaction with alcohols, I believe I told you that this reaction was called acid catalyzed esterification because it is. It is the formation of an ester. Oh, I'm sorry. Oh, man. No, I made a big dumb mistake. Really dumb. I'm talking about the reverse. Maybe it's okay to talk about it right now. But it's actually referencing this. Acid catalyzed esterification is called Fischer esterification. This is acid catalyzed hydrolysis. I'm sorry. This reaction is acid-catalyzed esterification. We're going to see that it's the same reaction going backwards. It's also called Fischer esterification. Actually, if you find the Wikipedia for Fischer esterification, it'll call it the Fischer-Smith esterification, but most textbooks leave out Smith. This reaction here, which is base followed by an aqueous workup to get back the carboxylic acid, this is called saponification. And saponification sounds a lot like soapifying, making soap.
Turning an OR group to an OH group?
Turning an OR group into an OH group, exactly. Although, actually, a little bit more balanced. Saponification oftentimes doesn't have that aqueous workup. It's just the OH minus portion. It leaves it with a carboxylate salt. And that carboxylate salt, if you run this on like a fatty acid, so you have a very long carbon shale and then a carboxylic acid on one end, saponification will take the ester group on that, convert it into a carboxylate, and now you have a hydrophilic head and a hydrophobic tail, and you've created soap. So if you want to make soap, you actually just take this first step. You don't add an aqueous workup, you leave it at the carboxylate. And that basic conversion from ester to carboxylate is called saponification. In general, I probably will not ask you directly about saponification, but I want you to have some connection about why these reactions are meaningful, not just in terms of chemistry and medicine and pharmacy. In terms of human evolution, humans have been making soap for a long time. They would take animal fat and the ash from their fires, and they would mix them together. The ash from fire had a lot of, that pot ash, as they called it, had a lot of potassium in it, which is actually where potassium get its name, is from potassium. The ion from potassium. And that potassium was bonded with hydroxide that it could form by reacting with the water. So you'd have potassium hydroxide, and you mix that with animal fat, and animal fat has a lot of fatty acids or a lot of fatty esters, and those fatty esters get saponified down to a carboxylate salt, and then they'd have soap, so they could hygiene themselves. All right. Sorry, that really didn't go the way that I envisioned it in my head.
The reverse way is esterification?
That's correct.
Okay.
So I got ahead of myself. For sure. All right, from the amide, we typically don't see this done in acidic conditions. It can be done. It's just far more common that this hydrolysis is run as basic conditions followed by acidic conditions. Strong basic conditions often means potassium hydroxide. And for the nitrile, same situation. Strong basic conditions followed by an aqueous workup. Once again, notice the trend from highly reactive to very little reactivity. Highly reactive hydrolyzes in any condition. Low reactivity needs strong basic conditions followed by aqueous workup in order to hydrolyze. All right, now let's look at the carboxylic acid going to form each of these reagents. To produce an acid chloride, we need the reagent thionyl chloride. What have you seen thionyl chloride used to do in the past? What have you used it for?
It's in our, one of our labs. I think it was in the deep.
It was to do that exactly. But we've seen it in class as well. Thionyl chloride is a nasty chemical. You learned that in lab. Who spilt it? It's scary. It's a scary thing to deal with because its byproducts are toxic sulfur dioxide and caustic hydrochloric acid. If thionyl chloride reacts with water, and it does, it's dangerous. But you've used it before in lecture in OCHEM 1.
Doesn't it add chlorine without rearrangement?
Yes. It avoids the carbocation intermediate. What does it add, though? It adds it from an alkene? Or does it substitute a group?
Substitute alcohol.
It substitutes an alcohol. And now for all of my students that always look at the carboxylic acid and say, what about the alcohol? Not an alcohol. But it is still an OH group. And in the same way, the OH of the alcohol can get substituted for a chlorine, like the OH of the carboxylic acid can get substituted for a chlorine. All right. So that's actually a repeat reagent, and it's doing pretty much the same thing we saw before. Substitute OH for Cl. In the formation of the acid anhydride, we'll use diphosphorus pentoxide, P2O5.
We learned about that?
You're learning it right now. This is referred to as a dehydrating agent. Any guesses why? Oh, it's not a dehydrogenation agent. It's a dehydration agent. It does take away an equivalence of H2O.
Where's the other H?
Where's the other H? Where's the other O?
You only need to take.
You need two equivalences of carboxylic acids. That means you've got OH and OH. And you combine them to make one oxygen, linking both carbonyls. You need to lose both H's and one O. So you need to extract H2O, dehydrate the structure. And it actually chemically dehydrates. So at the end of it, you get, I believe it's phosphorus acid, HPO3, twice. And it might be H2PO5, but I believe it's HPO3. Oh, you know what? That might not be right. I think maybe I should check on all that. I'm going to erase it, because I'm not confident. Cameron?
So did you say we need two equivalences of that carboxylic acid for the PTO5 to work?
Correct.
Okay.
Although, it's not that you need two equivalences. If you have a bucket of carboxylic acid and you drop P2O5 in it, it will take two equivalences. Yep. Good question.
Will we need to know the design of P2O5? Like in that kind of reaction, like will we know the shape of that molecule?
No. Although if you like went back to Gen Chem, we could try to derive that structure. What you might not guess is that the two phosphorus atoms have an oxygen linking them. So that P2O5, they both have two, and they're linked by an oxygen atom. Yeah, they basically like cleave themselves apart. Correct. Cameron?
So if it doesn't specifically say there's two equivalences, we can assume there's that left over as a byproduct?
If it, one more time?
So the R carboxylic acid, if it doesn't specifically say that there's two equivalences, there will be some of that left over when the reactions run through. So it would be like a byproduct.
Okay, yes and no. Rather than byproduct, we should call it an excess reagent. If I don't add enough P2O5, and quite honestly, we probably would add an excess amount of P2O5. But even if I just said this carboxylic acid and I don't have a coefficient in front that says 2, if I just say this carboxylic acid to this anhydride, it would be assumed that it's 2 to 1. You know, we spend a lot of time in Gen Chem talking about coefficients and balancing chemical equations. And in OChem, you hardly ever see a coefficient, even when there need to be coefficients. Because we just say you have as much of whatever you need to get what you want at the end. It certainly would be good to have that coefficient 2 in front. I'm hesitant to do it here. Well, maybe I could do it in red. I'm hesitant to do it here because then you might think that it applies to all of these reactions. If I do it in red, then it kind of speaks to the fact that it's only for this one. Is that fair? Good.
Real quick, we're drawing this out. I know this is a little different. You talked about formulas cleave. You have two different things, and the outputs are different. So if you
Backwards.
are creating that with a P2O5,
This is actually something I wanted to ask you. Yeah. Going this direction in red, do I make a symmetric anhydride or an asymmetric anhydride?
Symmetric.
The R group will always be the same. If it's two equivalences of this
okay, yes, sorry.
in the forward direction here, I will always make a symmetric anhydride. So P2O5, that's useful for making a symmetric anhydride. P2O5 is not useful if I want to make an asymmetric anhydride. And I'll talk about how to make an asymmetric anhydride.
Did you look up what it turns into?
Yeah, unfortunately, it's coming up with a bunch of pens. This is actually a good time for us to take a break. So why don't you guys get up and move around, get your blood flowing a little bit. And when we come back in, we'll look at the rest of these reactions. Oh, I was wrong. It doesn't form two equivalences of HPO3. I don't know if HPO3 exists. Oh, it's called metaphosphoric acid. You know what? That's the AI overview.
I was like, if you say it confidently, you're going to be more accurate than the AI overview. Thanks. I appreciate it.
Very true.
Yeah, Sigma Aldrich sells it. Metaphosphoric acid. I can't believe I called it phosphorus acid. That's like so lame of me. Everyone knows phosphorus acid is H3PO3. Goodness. Is it my first rodeo?
It might be.
It feels
I
like it.
haven't seen you at any of the rodeos. Okay, speaking of rodeos and my first rodeo real quick. Okay, I've been overthinking this, so I didn't submit it like a crazy person when I knew you would just grade it and totally bring it back. So, for this mechanism, this breaks it right here, right?
Correct.
Okay, I wanted to make sure before I continued and wrote it all
Breaks the
out.
ring.
Yeah, breaks the ring. So
Yeah.
now you have to do it, and then the next time you have it's not elimination, it's the one that's farther down on that list. That I'm trying to remember. Yes, that's what then splits it into the two molecules that you're dealing with at the end of the reaction.
Oh, it would be the next elimination step.
The next
This is the
elimination.
first elimination,
Yes, so it is the
and it
next
will
one.
be followed by an acyl addition,
Which will give you that
and then that will be followed by deprotonation. And then you'll be at the hemiacetal. You'll have a gem ether all. Then you do another protonation, another elimination, and that's when you'll finally get two structures. And then after the second elimination, one more deprotonation.
Okay,
Yep, you got
perfect.
it.
I was overthinking it, and I know when I read it out wrong once, it sticks with me, so I actively try not to do it. And then this one, I think I
need steps.
skipped a step.
You need first, second.
Because it says 3. Can I just jump in? With each
Oh,
one?
it's 3 points.
Yeah.
1 point, 1 point, 1 point.
Okay,
3 points.
Sweet.
Great job.
I was like, if this is a break, I'll lose my mind.
Do we have a unit test this week?
You do have a unit test this week. It's been a while.
It's been a while. It's been a very relaxing while.
Do you know how far away the
4 weeks?
I'm a very good technical brain.
We have only 2 more unit tests?
Is this our last midterm? Or is there one
We don't
more?
have. Well, you just have the one midterm.
Sorry.
No,
One
two more
two
unit
more
tests.
unit tests, then the final.
Oh.
There'll be a unit test the weekend after Thanksgiving.
That's why I said it. That. Okay.
Yeah, absolutely. Not sure what made you think of those, but those work great. I think we do have some risk, I guess, of which carbonyl would actually react with this, but it's certainly plausible. I like it.
Yeah.
I like it a lot.
I know you were
actually.
saying something about like last time with the acid chloride. Probably.
No. No, I was. You were thinking about acylating this top engineering, and I said that one's not. as
Phosphorus.
active
Okay, it's
as
nitrogen.
this one.
Yeah. Okay, that's what you were saying.
Yeah. No, this looks great. Good job.
Okay. Cool.
And if you want to
just keep
play
it
around
going?
with those other reactions that you were thinking of, you're more than welcome to.
I have the other one saved at home. So
Yeah.
maybe I'll just send it to you in an email and see like what you think of it.
Absolutely.
But
This is your playtime, basically.
Yeah. I probably won't resubmit it for.
That's
anything.
fair.
I'll just
Yeah.
keep it like that, but yeah.
Double bonds to your oxygens. What the hell? Work. Yeah. No one likes it though. Double bonds.
This is nitrogen.
Double bonds.
And what's the D shell?
This structure has a 4- charge. Did I say P2O5 4-?
Yeah, you did.
Well, joke's on you. That's not how I write my 4-. All right, breaks over. Draw the structure of H2PO6. Nah, just kidding. I couldn't. Well, there's a lot of possible answers.
Yeah, that's true.
Yeah, that's the biggest problem. Honestly, without having looked it up, I might not have guessed this one. I might have guessed something similar. I think I don't know. I don't know. No, I probably wouldn't have gotten there, to be honest. It would have been a while. All right. Why did you only double bond those carbons? Those oxygens too. Yes, there you go.
This
It's a nitrogen family. That makes it a nictogen. Where'd you get those numbers from? Okay, so this is called metaphosphoric acid,
Did I get it right?
and it's not the product.
No.
That's what I predicted. That's what I said, but I'll show you guys what it is.
It's the same thing. They just swap. You see? You don't like my 4- charge?
No, that's not how I write 4- either. Good guess. Actually, I wonder if I can find the name of that compound for you guys, since I know you're so interested in it.
You've been hyping me up. I really invested, yeah. You're like, oh man, I would never get this. I would never get this structure. Okay.
You wanna try quick before I show you it? All right, here's a there's a really cool one. This is not the same structure, but doesn't this look cool?
Whoa.
Phosphorus pentoxide.
There's too many phosphorus.
Why would it be called phosphorus pentoxide? There's 10 oxygens
And 4 phosphorus.
and 4 phosphoruses.
Should it be 2.5 oxide?
Anyways, here's the name of it. H2P2O6 is the dehydrated product. and it's called dihydrate of hypophosphoric acid. So that's not lame at all. But here's the actual structure. It is one of the phosphorus atoms. Whoa, why can't I see it? One of the phosphorus atoms takes two OH groups. That means that it took both H's, one H to one of its already held O's, and it took an OH. The other phosphorus didn't change at all. Killian has kindly drawn for us what P2O5 looks like in its precursor. And after hydrating itself, after dehydrating the reaction, it becomes this. Not something I'll ask you to know, but interesting nonetheless. All right, to the ester. We have already seen this reaction. This is what I wrote in green earlier. Fischer esterification. We need an alcohol and acidic conditions, ROH, H+. This is Fischer esterification. I don't like that name because it doesn't tell you anything about what it does. Well, I guess it does a little bit. At least it's not just called the Fischer reaction. But the acid catalyzed esterification is a great way to get there. The next reaction, running out of colors to use. The carboxylic acid to the amide. This also, similar to the anhydride reaction, requires a dehydration product called DCC. And then we run this with whatever amine we are looking for. Since my generic amine is written as NR2, we need to at least have one hydrogen on this amine. That means you could go from ammonia, NH3, to a primary amine, NH2R, to a secondary amine, like this, but you could not use a tertiary amine. DCC.
Have we used that before?
No, but a lot of students will mistake this with what other reagent?
PCC.
PCC. Makes sense that it's easily confused. DCC is also a dehydrating reagent. DCC has a pretty cool structure, in my opinion. Do you guys remember what the CY stood for?
Cyclohexane.
Cyclohexyl. Good.
Fat.
So this is dicyclohexyl. Yeah, I always forget the last C. It describes the fact that the carbon is bonded to both nitrogens. Dicyclohexyl carbodiimide. Yes, sir.
Is that DCC and HNR2 at the same time, or one or the other?
Both.
Both at the same time.
You need the amine to substitute the carboxylic acid for the amide. That's where the amide group comes from. DCC allows for the reaction to proceed by pulling out the water. It's also a dehydrating reagent. So we saw how P2O5 becomes H2P2O6. DCC DCC becomes this, which I don't know that I know the name for sure, but it very well might be called N' dicyclohexyl urea. Urea is a diamide, where you have a one carbon carbonyl with NH2 on both sides. Can you see how the water is pulled out? Sure enough, this calls it a urea byproduct. Here are the two H's of H2O. Here's the oxygen of H2O. Now, if we were to try and propose the mechanism, also, if you find this mechanism on active, would you please message me? Because I think I've accidentally left it in there once, and I've tried to pull it out. I used to test on this mechanism. If we were to look at the mechanism, we've got nucleophiles at the nitrogens in the presence of an acid. So our first step is nitrogen deprotonating the acid. If this nitrogen becomes protonated, it makes this carbon much more electrophilic because now nitrogen wants to break its bond back towards itself. The electrophile is carbon, which means the nucleophile is the carboxylate that is present. So the carboxylate will bond to the carbon. That's how we get an OC bond to start us towards our final product.
C becomes positive?
C has a strong partial positive. Let's look at the mechanism on the screen actually. Nitrogen becomes protonated. And then we form this carbon-oxygen bond. This is where whatever amine we've had comes into play. The amine now starts to substitute on the carbonyl carbon. And then we have elimination of our dehydrating product. But that leaves us with a protonated amide and a deprotonated urea byproduct. And so then there's just acid-base chemistry, a proton transfer. I'm not going to ask for that mechanism because most of it involves DCC and it's a little bit convoluted. It's hard to draw for sure. But it follows a lot of the similar chemistry we saw with acetals and imines, where you've got deprotonation, basically acyl addition. Then you have another acyl addition, an elimination, and deprotonation. Okay, back to this. We have formed all of our groups from the carboxylic acid. The only thing left to form are the individual derivatives from the other derivatives. The first one is the acid chloride. Being the most reactive of the carbonyls, the acid chloride can essentially form all of the other less reactive carbonyls. The acid chloride can react to form an anhydride by reacting with a carboxylate. This is simple substitution, acyl substitution. The carboxylate attacks the carbonyl of the acid chloride and then kicks off the chlorine as a byproduct. 2 steps. This allows us to do asymmetric very easily. But there's no reason that you can't also form symmetric anhydrides this way as well. The acid chloride can also be used to form the ester, and the anhydride can also be used to form an ester. Instead of having a carboxylate to get me this new group, to form an ester, what I want is an alcohol, ROH, and I need something that is good at deprotonating the alcohol once the reaction is over. What happens in this mechanism is that the alcohol substitutes the chlorine, and it stays as a protonated ester in the presence of chloride. But chloride is not a good base, so it doesn't deprotonate. So we also add pyridine to this reaction. Remember that pyridine is the benzene-looking structure with a nitrogen in it. We can abbreviate that as pyridine, PYR, or you can spell it out, pyridine, or you can draw it.
Why do you do it?
Why do we need it?
Yeah.
It acts as a base to yield the final product. Prior to this product, there's a protonated ester, and pyridine is a good base to deprotonate that. Maddie?
Just so I make sure I didn't miss it, the line that is going in between, that you have the asymmetric portion, is that also where RH and pyridine go, or they can switch between those two? Yeah. I guess I'm just kind of confused by that line.
Oh, the carboxylate can also react
Okay.
with alcohol and pyridine. To be fair, the carboxylate, or the anhydride, I apologize. Was that your confusion? The carboxylate is not reacting. The anhydride is reacting. Okay. I've got my arrow in the wrong spot. I've got it in the wrong spot on there too. Okay, instead of having this arrow that connects this line here, it should be from this group here. It should be written as this group can also react in this way. You know what? I thought the line looked weird when I made it, and now I understand. It should not be a line connecting these two arrows. It should be a line connecting this functional group to this functional group. Cameron?
So RH and pyridine will result in the same product for both of those starting groups?
Correct.
Okay.
Here it substitutes a chlorine. Here it substitutes an entire carbonyl group. But the acid halide and the acid anhydride are both equally capable of being substituted to form an ester. Those of you that took Gen Chem 2 lab here did this at the end of Gen Chem 2 lab when you synthesized acetyl salicylic acid. You took acetic anhydride and the alcohol of salicylic acid substituted one equivalence of the carbonyls and created a carboxylic acid byproduct. You got a question?
How do you get from what's the top one called?
The acid halide?
How do you get from the acid halide to the acetic acid anhydride?
You react the acid halide with the carboxylate to generate an acid anhydride.
It's a carboxylate.
A carboxylate is a deprotonated carboxylic acid. RCO2 minus.
Oh, you're not saying add two of them. Oh, okay.
Our last reaction here is to form the amide. To be fair, you can also form this amide from the acid anhydride. It's just less common. What we add here is whatever amine is necessary. So once again, we write it very similar to how we make the amide. Whatever amine is necessary. And instead of adding pyridine to act as a base, pyridine is a good base because of the nitrogen. We have a nitrogen. So we just make sure that we add this in an excess amount, and we don't need to add pyridine as well. Alcohol needs pyridine because alcohol is not a very good base. Amine doesn't need pyridine because the amine is a good enough base. Our last reaction on this diagram is to take the amide to the nitrile. And what we use here is P2O5. Bye, Kayla. We've used it before, right?
Yeah.
There is a caveat. This must be a primary amide. It must be a carbonyl connected to NH2. And now you can see why a dehydrating reagent is useful. Pull the H2 off of the amide and the oxygen off the carbonyl, and you've pulled out H2O to leave behind a nitrile, CN triple bond. All right, one other reaction I want you to add to this diagram is actually the synthesis of the nitrile. This is a review. how can you make a nitrile? We see now that we can make it by dehydrating a primary amide. How else can you make it? We do this in OCHEM 1. What did you say?
Is it reduction of thermal or something?
No. Although maybe you're thinking of like NaNH3 reduction.
Yeah.
No.
SN2.
SN2 with. Good. So if I have something like Rx and I introduce cyanide, substitute that halogen or that good leaving group for a cyanide, for a nitrile. That's review. We've been doing that since OCHEM 1. Now we're seeing that we make that nitrile and we can now turn that into a carboxylic acid. All right, any questions on this horrendous diagram?
So you have to get that cyanide from cherry pits.
I don't know. Any other questions?
Can you make the cyanide in the lab? Do you need an organism to make it? What's an easy way to make the CN ion?
I don't know how to make the CN ion. Should we look into it later?
Yeah.
We've got some more new reactions here. Notice that these next two diagrams, they actually have the same reagents. It's first an excess amount of phenyl grignard, followed by an aqueous workup. And the excess amount is important here. First, it's really hard to control the organometallic to be the limiting reagent. It's easier if you can just make it the excess reagent. Second, if you are trying to limit the Grignard, you can't always be confident that all of the other molecules, the reactant molecules, will only react once with the Grignard and not react twice. It's very common they react twice. I actually want to start with the reaction on the bottom. The two functional groups that can react here to give us this product. I also want you to notice there's a bit of a similarity between the products of these two roadmaps, or these two diagrams. They have the same carbon chain, and they have a different number of pH groups. Okay, since this bottom one only has one pH group, we should assume that that came from the Grignard attack. That means that this is the region that has chemistry going on. Here I have two pH groups. Why did I put that as O minus? I don't know. Because there's an aqueous workup. It's not O minus. Thank you. I read your mind.
Yeah, thanks.
An excess amount tells me I'm getting two equivalences. Down here, the functional groups that leave me with just a ketone, where whatever R group I've added is attached once as a ketone. These are the amide and the nitrile. Yes, sir.
I guess, wait, no, I guess that makes, never mind.
When the amide and the nitrile get attacked by the organometallic, they create this tetrahedral intermediate. Well, actually, this one is a trigonal planar intermediate. But they create an intermediate that has no good leaving group. It creates an intermediate after acyl addition, and it can't kick off anything. It can't kick off O minus. It won't kick off a CN bond. Those are very strong. And now it has a new R group attached. Here, it gets a CN double bond and the new R group. Nothing to kick off. So then during the aqueous workup, we basically have the imine hydrolysis process. We hydrolyze these imide intermediates and we get back to a ketone. This is reminiscent of imine hydrolysis. All of these other groups, they do have a good leaving group, which means that when these groups react, they actually kick off a leaving group and create a ketone intermediate, and ketones, as we know, are already reactive to Grignard additions. So they get reacted twice. So we have the acid halide, the acid anhydride, and which other one? You've got two options, carboxylic acid or ester. Carboxylic acids deprotonate in the presence of Grignards. Carboxylic acids don't react with Grignards. So we get the ester.
On the cyanide one, you're taking the oxygen from the water to make that carbonyl.
Can you say that one more time?
For the cyanide one, you're taking the oxygen that becomes the carbonyl from the water.
That's correct.
So you have 3 hydrogens roaming around?
Maybe. There is a byproduct, ammonia, NH3.
Yes, there is.
These all have an intermediate that looks like this. That's because the acid chloride kicks off a chlorine after the acyl addition. The anhydride kicks off an equivalence of the carbonyl after the acyl addition. The ester kicks off an alkoxide, OR minus, after the acyl addition. So some byproducts that you get left with, this leaves you with a carboxylic acid. This leaves you with, this leaves you with an alcohol, a carboxylic acid, and a hydrochloric acid byproduct. Killian had a good question. Down here, you're left with a byproduct of ammonia or a byproduct of amine. And Killian, if you're interested in seeing these intermediates, this intermediate has nothing good to kick off, but that's essentially a deprotonated imine, and we know that imines get hydrolyzed back to aldehydes and ketones. And this has an intermediate and this is also reminiscent of the imine hydrolysis mechanism. Once that gets protonated, it hydrolyzes back to the ketone. For those of you that are interested, here's one of those intermediates, a tetrahedral intermediate where the Grignard has done acyl addition, but now this collapses to reform the carbonyl, and it kicks off a good leaving group. It's just that the leaving group is different for each different starting material. All right, 2 last reactions I wanted to look at. These involve the ester. Oh no, there were a couple others. Doesn't that suck? Oh, you know what? These are the same reaction. I wanted to have you guys see two different versions of it. This is trans esterification. We can do esterification with an alcohol and a carboxylic acid, but we can do trans esterification with an alcohol and an ester. So here I have this phenyl acetate, but I can make this methyl acetate by reacting with methanol and H+. It's substituting the ester group for a new ester group, methyl acetate. Or we could take an alcohol like sec-butyl alcohol and we can make sec-butyl acetate. Phenyl acetate to methyl acetate, phenyl acetate to sec-butyl acetate. Taking an ester and converting it into a different ester. These reactions are not good at equilibrium. Fischer esterification is not good at equilibrium. Fischer esterification produces a water byproduct, and that water byproduct can hydrolyze the ester that forms. So the equilibrium is hard to manage. These are equally hard to manage. As soon as you substitute one alcohol off, you have the potential of just trans-esterifying it back to the ester you made. You now have the same conditions to do trans-esterification backwards. So this is a really equilibrium-heavy reaction. It's hard to control, but it can be useful if you have an ester and you need to transfer it into a different ester. All right. One thing that we have not reviewed with all of these derivative reactions, and perhaps that's my fault for not making a diagram to show this, except that we already did show it. Let me show you how we did. Back in the Unit 3 with alcohols, synthesis of alcohols, we showed, please tell me this is here. Oh. No, I didn't make it on this worksheet. We showed how the acid chloride, the acid anhydride, the ester, and the carboxylic acid can all be reduced with LAH and an aqueous workup down to an alcohol with some byproducts. The HCl had a byproduct of, or the acid chloride had a byproduct of HCl. This actually just formed two equivalences of the alcohol. This formed a variable alcohol. It's always going to form whatever this group is plus whatever this group is. And then this had a byproduct of water. So we've seen the reduction of all of these groups already, but we haven't seen the reduction of the amide and the nitrile. So that's what we're going to look at right now. Can you guess what functional group they don't form? Alcohol. Because otherwise I would have given that to you. They don't form an alcohol. Let's look at them in order. Let's take acetonitrile and we'll reduce it with LAH followed by an aqueous workup. The product that we make is ethylamine. CN bonds are very hard to break, so they don't. In this reduction, when I add hydrogens to the carbon, I keep the CN bond. If I have something like a primary amide, the primary amide, unlike all of these other groups, which have some sort of cleavage, the CL bond cleaves, the carboxylate cleaves, the alkoxide cleaves, the hydroxyl cleaves. There's no cleavage in these. The carbon chain stays entirely intact, and you reduce amide directly to amine. Primary amide, primary amine. How would you describe the substitution of this amide? Secondary amide. You can also describe it as cyclic. Do you remember what we called cyclic esters? Killian remembers. You were upset at me for it all. No. Cyclic esters we called lactones. Cyclic amides we call lactams. Same thing happens. The carbon chain stays entirely intact. None of the CN bonds break. Secondary amide gets reduced down to a secondary amine. All right, who remembers the name of this amide? So one carbon carbonyl, so it gets the root form. And the suffix
Formamide.
amide, formamide. How would you describe this substitution? This is a tertiary amide. It's bonded to 3 carbons. So the product is a tertiary amine. This is trimethylamine. That's it. Those are all of our reactions for this section. Congratulations, you survived. The only thing that we need to do to prepare you for your unit test is mechanisms. Here are the mechanisms that I'm going to ask you to be able to show me from this section. So this is in addition to acetal formation and acetal hydrolysis. I'm also going to ask you to know Fischer esterification and ester hydrolysis, specifically in acidic conditions, the inverses of each other. I'm considering having bonus problems that show other mechanisms
On the test?
on the final exam. So I want you to be aware of other mechanisms that might come up.
What was the fourth mechanism you said after esterification?
Fischer esterification and ester hydrolysis in acidic conditions. Does that mean that all of these other mechanisms are too hard? Tedious.
Yeah.
It's incredibly tedious.
It's like biochem reactions and you do all this.
That's true.
It takes forever.
It takes a long time.
Yeah.
Well, we saw the acetal formation and the acetal hydrolysis took a long time too. And it's just tedious. So that's a possibility of 4 mechanisms that you might see on your unit test this weekend. Wednesday we'll do the esterification reaction ones. I had another activity for us today in case we got through stuff soon enough, but we didn't really. So I think I'll keep this unless you want to work on something while you're away. Yeah, that sounds about right. On Wednesday, if we get the time to, and I might break up our work on mechanisms to do this because the mechanisms get a little overwhelming and the same. This is a synthetic pathway problem. I'm asking you, I'll upload, well actually this is uploaded. This is on the, it's on the document already. So you can already find this on Canvas. I'm asking you to pick a functional group, show a reaction from this unit, aldehydes, ketones, carboxylic acids, and derivatives, and form a new product. And then take another reaction and form a final product, and then take 3 of those 5 pieces of information out. So you've got 3 structures, starting material, intermediate product, 2 reactions, and I want you to pull 3 of those pieces of information out, and then you're going to swap. I'm going to have you guys do this in groups so that you can brainstorm with other people, and I'm going to have you swap with other groups and solve those syntheses. So be thinking about that, because that's an activity I want us to do on Wednesday. You're right, Thursday. Yeah, it's been a long day. And one of the reasons is you don't need to be smart about molecules. You don't need to know what molecules exist to be able to brainstorm and be creative about how to transform functional groups. That's really all it's about. At the same time, you have another written work that's due Thursday. I think on Thursday, when we do mechanisms, we might practice with one of the written work mechanisms. Because that can take a while. So if you're going to get started on written work, start on the synthesis. All right? Have a good night, guys. See you Thursday.
Yeah, Merle. Have you already come up with the amount that you want to use? Follow the procedure, what they say. Follow the recipe.